Exercise 69, question 9, page 136. Use of Newton-Raphson iterative method to find the root of an equation. In this particular case, we've got this function and we're trying to find the root near to 4.2, correct of three significant figures. And the magnitude y of the oscillation is 0. So in other words, we know that this equals 0, which it needs to do for Newton-Raphson to work. So we've got that. The function that we're going to put into the Newton-Raphson formula is this, minus 7.4 e to the 0.52 sine 3t equals 0 at this particular root. So we're okay to use this. So we've got the function that we can put into Newton-Raphson here. All we need to do now is find the differential, which is this part here. So we need to differentiate this function and then put our first estimation for the value in, which is 4.2. If we look at this, the differential can be written down. This is a two-part function. T appears twice, and so we've got one function involving t here, multiplied by another function, the sine function here. And you must remember, I hope, that this involves using the product rule. If you need a reminder, look at the notes, look at the video clips on the product rule for the method of differentiation. But what we need to do, what we remember from the product rule is, all we do is we take the first function and multiply that by the differential of the second function, which is this one, and then add the second function and multiply that by the differential of the first function. So we can pretty well write it down, especially when we remember differentiating exponential functions like this. The power remains unchanged, but any number that's in there comes down and multiplies by what's in front. And also we remember that in trigonometric functions like this, sine becomes cosine and the 3 comes out and goes in front. So that's what we need to remember, and we can then write down the differential, which is the differential function is, so the first function, minus 7.4 e to the 0.5t multiplied by the differential of the first function, which is 3 cosine 3t, and then we add the second function, which is sine 3t, and multiply that by the differential of the first function, which is minus 7.4, so I put it in brackets, times a half times e to the 0.5t, just about room. So now, if we look at it, and this is often the case with functions that involve this exponential function, once differentiated, they don't change, so that can, both of those terms can be removed from the bracket. And looking further, we can see that minus 7.4 is common to both terms. These two terms here, 1, 2. So minus 7.4 and e to the 0.5t is common to both. So we can take them outside the bracket. Minus 7.4 e to the 0.5t. And now what am I left with inside the bracket? I ask myself the question, what have I got to multiply this, which I've removed, by to get back to this first term? Hopefully you can see that that's just for 3 cos 3t. So 3 cos 3t. And then I ask myself, what have I got to multiply this by to get back to this? And so we've got the minus 7.4 e to the 0.5t. What's left is 0.5 times sine 3t. But that will be plus, because we've got the minus sign outside. So plus 0.5 sine 3t. If you want to make sure that you've done that factorisation correct, multiply out the brackets. Check that this times this gets you back to the first term, and that this times this gets you back to the second term, and you'll find that it does. We'll see in a minute that it's well worth factorising this. So now let's put this into Newton-Raphson, which is that. The second approximation, or our second approximation to the root, equals R1 minus the value of the function at R1 divided by the value of the differential at R1. So this equals R1 minus, now the value of the function is minus 7.4 e to the 0.52. Now let's not put the value in yet, or e to the 0.5 R1 rather. Multiplied by the sine of 3 times R1 divided by the differential, which is minus 7.4 e to the 0.5 times R1 times 3 cos 3 R1 plus 0.5 sine R3 R1. And hopefully you can see that usefully these cancel, which really simplifies our iterative approach. So R2 equals, in fact, R1 minus the sine of 3R1 over 3 cosine 3R1 plus 0.5 sine 3R1. Much more straightforward. So now we put the numbers in. R2 equals 4.2 minus the sine of 3 times 4.2 over 3 times the cosine of 3 times 4.2 plus 0.5 times the sine of 3 times 4.2. Worth leaving it like that in the calculator rather than working out, which we could do easily, what 3 times 4.2 is. Worth leaving it like that because we can then, if we leave this in the calculator, this calculation when we've done it, we get our next root. That then becomes R1, and so we can substitute these numbers in. We can just keep the calculator in its calculation there, and then just go along using the scroll button and change 4.2 to whatever the next root is. The only other thing to remember is that these are assuming we're in radians in the calculator, so check you're in radians in the calculator. These are not degrees, and you should then be able to finish the problem off and find that the root to 3 significant figures is 4.19 as suggested in the question.